Imagine trying to do long division using only Roman numerals. You can't just carry a remainder or shift a decimal. To do any math at all, you have to physically add and subtract distinct, rigid symbols. The archaic Greeks ran into a deep philosophical block with the idea of empty space. Their core framework for reality was tied to physical geometry, which led to a troubling question. How can not being actually be? If something doesn't exist, you can't measure it, so to them, it couldn't be a number. Without a way to represent an empty quantity, early scholars hit a hard limit. They managed to build aqueducts and chart planetary movements, but advanced engineering and complex arithmetic require a reliable way to calculate the absence of value. To push mathematics forward, thinkers had to break that psychological barrier. They had to take the intellectually uncomfortable step of giving nothing a specific name, a written symbol, and a mathematical value. Record keepers in Babylon and Mesoamerica reached a point where tracking vast calendars and trading goods required a way to signal a completely empty space. They needed a structural punctuation mark for their positional notation. This animated diagram shows how those positions work. If you have 2 shapes in the hundreds column and 5 in the ones, you need a way to show there are 0 tens. Drop an empty circle into that middle column, and 25 instantly becomes 205. But at this stage, the circle is strictly a placeholder. It tells you a column is empty, but it isn't a true number itself. If you try to add or subtract that empty circle on its own, the calculation simply doesn't compute. Having a symbol to hold an empty space is useful for counting, but doing actual arithmetic with nothing requires a different logical leap. That leap happened in ancient India. Indian scholars were comfortable with the concept of shunya, or the void, treating emptiness as a tangible presence. By the 9th century, we see the zero glyph explicitly carved into stone at sites like the Chaturbhuj temple. Mathematicians like Brahmagupta formalized the rules for treating 0 as an active number. He established that adding 0 to any number leaves that number unchanged, and if you multiply any number by 0, the result collapses to 0. They also tackled the strange mechanics of division. Because 0 has no multiplicative inverse, meaning no real number multiplied by 0 produces 1, dividing by 0 breaks standard arithmetic logic. It results in an undefined or infinite state. By defining exactly how 0 behaves in an equation, scholars shifted it from a passive placeholder to an active participant, providing the logical basis for algebraic manipulation. This functioning 0 soon traveled into the Islamic world. By the 9th century, scholars like Al-Khwarizmi were synthesizing Indian and Greek knowledge, integrating the 0 into comprehensive astronomical tables and algorithms. From there, the Hindu-Arabic numeral system moved across the Mediterranean. In the 13th century, an Italian mathematician named Fibonacci learned the system along North African merchant routes and published it for a European audience. Before this, European merchants were still manually sliding beads on an abacus and recording results in Roman numerals. The new system allowed them to perform complex addition, multiplication, and root extraction quickly on a single sheet of paper. By marrying the structural utility of a column placeholder with the actionable math of a true number, this 10-digit system removed the physical barriers to human calculation. In the mid-20th century, as early data processing emerged, 0 took on a new physical form. It stepped off the written page and became a literal state of electricity. This is the foundation of binary code. In digital electronics, the number 1 stands for the presence of an electrical current. The number 0 represents the direct absence of that current, the off state in a circuit. Computer scientists also adopted zero-based array indexing. In many programming languages, when you sequence digital data, the very first position in the list is numbered 0, not 1. The count begins at the void. This role makes 0 the structural architecture used to build and execute modern software. Today, algorithms built entirely on binary sequences of 1s and 0s process over 400 million terabytes of data every single day. The ancient Greeks looked at empty space and saw a philosophical impossibility. But by choosing to quantify that void, to name it and give it rules, humanity developed the exact mathematical language required to build the modern world.